Hi again. Today we're going to talk a little bit about bonding. And so, as I had told you in the last video, I was going to go in a little bit into more detail. So, from before, we talked about the bonding of hydrogen atoms, and two come together to form a bond. And I said that that bond is more stable. And sometimes you just have to believe me, or sometimes I can show you a little bit about why that's the case. So, if we look at a diagram of energy on the y-axis and the distance between the nuclei on the x-axis, you can see that when these two nuclei are really far apart from each other, that they don't recognize that they're near each other, and there's no energy difference, as if they were just a hydrogen atom floating around in space, let's say. But as they start to get a little closer, they end up starting to feel attractive forces between each other. And why are they being attracted to each other? Well, there's an electron on one atom, and it's attracted to the positively charged nucleus of the other atom that's nearby. And as they get closer and closer, that energy stabilization becomes greater and greater because they're now being shared between the two nuclei, and these electrons are now sharing a molecular orbital between the two. But if you get too close, you start to rapidly increase the amount of energy, and so you're effectively pushing the nuclei toward each other. And so the Coulombic repulsion, that is the positive and positive, is like trying to smash two magnets against each other. And again, that energetically goes very, very high. Now, there are two real key pieces of information that you can get out of these types of diagrams. This diagram is also called, you might hear it called a Morse potential. That's what this is called. So the first is that you can find out the bond dissociation energy. That is the amount of energy it takes to get the two hydrogen atoms, in this case, to completely dissociate back to H dot and H dot. And that's found by measuring the distance from this zero line down to near the bottom of this well. The other bit of information that you can derive from this Morse potential is the bond distance. And so again, this is this x-axis is the distance between the nuclei. So from 0 to whatever this point is here, this tells you again how far apart the nuclei are. We call that distance the bond length. So out of one graph, you can get the bond length and the bond dissociation energy. Now, the textbook that we work with doesn't talk very much about these these Morse potentials, but I think it's nice to have a framework of where the idea of bond dissociation energy comes from. So one thing that's really important to recognize in organic chemistry is that not all atoms are created equal. So one of the key features that makes them different that we can look at as organic chemists is their electronegativity. So electronegativity is a scale that was developed by two different chemists, really, but we like to typically follow the Pauling scale of electronegativity. It's a scale that was used to determine how much of a pull a nucleus would have on electrons. And as I told you before, you go from, in the bottom left, from being less electronegative, I'll abbreviate that as En, to being more electronegative. So, and it goes from bottom left to top right. And so if you look toward electronegativities, you could say that oxygen which is here, is more electronegative than carbon, which is here. And so let's look at the ramifications of that in terms of bonding. So again, oxygen is more electronegative, and because it's more electronegative, it's going to be lower in energy it's going to have lower energy orbitals where the electrons are being occupied. And so we can draw this as being a little bit lower on the energy diagram than carbon. And again, carbon is less electronegative, and so it's going to be a little bit higher than, this orbital will be a little bit higher than that of oxygen. And so when they form a bond, the two atoms are actually not going to share these electrons equally. Oxygen is closer in energy to this orbital, it's going to have more of the electrons residing on the oxygen atom as opposed to on the carbon, or the oxygen nucleus, as opposed to the carbon nucleus. And when that occurs, we call this a polar bond. We can also use this type of symbolism where we have a delta negative, meaning it has a partial negative charge, and a delta positive, meaning it has a partial positive charge. Another way that we like to draw this kind of bond polarity is by drawing a bond dipole moment, and that's signified by this little arrow. You'll notice at the bottom of the arrow, or at one end of the arrow, there is effectively like a little plus sign, and that's how I like to think about it. It is a plus sign. It's on the positive side, and and you can think about the arrow as pointing to where the electrons would want to be. So that is toward the electronegative atom. That's all for right now. Thanks.